Hello grade 11s, sorry that I can't be in our lesson today. I'm making a short video now to go through the notes for day 6. Hopefully you will remember that we actually have done day 5 already. We looked at what a radian was. We looked at this way of measuring angles with a measure that is not a degree but a radian. And we also looked at arcs and sectors a little while ago. So it will be something to review. But it is, we're going to move on from there. So we're going to move on to day 6. We're going to look at something called the unit circle, which I'm sure will be somewhat familiar to a lot of you. And we're also going to look at the sine curve and start looking at trig functions. I think this might be a review for a lot of you, but I am not going to assume that everyone has knowledge of this. Obviously, feel free to pause the video and work through it if you're really confident, and then just use the video to check your answers. You can stop at any point and try some questions out, and then unpause to check in answers with me. So I will go through this now. So there is a starter first of all, which is just reviewing what a radian is basically. On the diagram of the unit circle below, so a circle with a radius of 1, hence it's called a unit circle, the points A, B and C represent angles of 90 degrees, 180 degrees and 270 degrees. Just a quick reminder, all angles are measured from the positive x-axis and they're measured anti-clockwise. If you want to, you can try and research a bit and find out why that is. Why isn't it clockwise like a clock, like we tend to think of as our default? Okay, so write 90 degrees, 180 degrees and 270 degrees in radians. Now, our key conversion that we need to remember is that pi radians is equal to 180 degrees. Okay, so 1 pi radians is equal to half a turn. So that means pi radians would be down here. So let's not do 90 first, let's start with 180. So these are all degrees, and I'm going to do my radians next to them. So 180 degrees is pi radians. That means 90 degrees must be half of that, because 90 is half of 180. So I'll write it as pi divided by 2. And we'd say it, when we're talking about it, as pi by 2. That's the convention of how we say that number. So that's pi by 2. That's half of a radian. And so C, we've gone another half of a radian round. We're 1.5 radians round. And we would write that using an improper fraction as 3 pi divided by 2, and we'd say it as 3 pi by 2 radians. Okay, question 2, where might you place 225 degrees? Well, we know 180 degrees is at B, 270 is at C, 225 is exactly halfway in between. So that would be here, 225 degrees. That is anti-clockwise from the positive x-axis. Where might you place 360? Well, we've done a full turn, so we're back to the start. So this would be 0 degrees or 360 degrees. Or if we went round a second time, I guess it would be 720 degrees. And then where would we place 3 pi? Well, let's have a think. I'm going to draw this one on. 1 pi took us round halfway around the circle. 2 pi will take us all the way around the circle. And we need to keep going. We want to get to 3 pi. So 3 pi is over here. Thinking about it as going round a circle, we've actually in the same place as pi. So you can see they will start, we'll get to the same points. We can keep going round the circle as many times as we like. I'm going to get rid of that. Moving on to number 3, we've got some negative angles. Now we consider a negative angle as clockwise. Positive angles are anti-clockwise. Negative angles are clockwise. So negative pi by 2. Positive pi by 2 was up the top of the circle. So negative pi by 2 will be down the bottom. If you are struggling to think in radians to begin with, you can think of it as moving negative 90 degrees. Negative 45 degrees, we're moving clockwise, so it's going to be around about here. And negative 400, that's a bit trickier. So I'm going to draw it on again. Negative 400, I'm going clockwise. I'm going to do a full turn. That gives me 360. If I want to go up to 400, I need to do another 40. So it's not quite going to get to negative 45, is it? It's going to be about here. Maybe even closer than that. It's a bit tricky to draw that one on accurately, isn't it? Okay, just a bit of brief review on radians. All right, if you need to, you might find you actually want to go back, review some of the day 5, maybe have another look at some of those questions on radians and make sure you're confident with them. We're going to be working an awful lot with radians as we go on with this unit and actually the rest of our course. You'll find that most of the work we do relating to angles is to do with radians. Okay, we're going to move on a little bit. What we're going to be looking at are things called periodic phenomena. Those are things that follow some sort of periodic motion, so they repeat themselves. So that you can see are things like tides or orbits. We model them using periodic functions, and the one we use most often is the sine function or the cosine function. You'll see that they are very similar. And you'll see that we have it written here, f of x is equal to this. We've got 4 parameters, a, b, c, and d. We're going to investigate a little bit about these over the next few lessons. But this is our conventional setup. So if we're going to be able to do this modelling, we need to think a little bit about what's meant by sine of a number bigger than 90. We've been introduced to sine, cos and tan as to do with triangles, and really we can't have angles bigger than 180 degrees in a triangle, so we're going to consider those a little bit, and we're going to go back to this unit circle. You might find for this you want to stop, do some of the questions, and then unpause me and check your answers, maybe fast forward me, I'd want to fast forward me, and check some of your answers, so feel free to do that at any point. From the unit circle, explain why cos theta equals x. Okay, so looking at this unit circle, I've got theta marked here in this triangle, and I'm just going to think, well, if I'm talking about cos theta, cos is the adjacent, this side's the adjacent, divided by the hypotenuse. So cos theta is adjacent divided by hypotenuse, and in our triangle, the adjacent side is called x, the hypotenuse is 1. So that simplifies quite nicely to just cos theta equals x. Similarly, sine is opposite divided by hypotenuse, so it would be y divided by 1, which is just y. So sine theta is equal to y. So what that means is we can actually consider sine theta as theta gets bigger and bigger as just what the y coordinate is doing as we move around our circle. And we can think of cos theta as what the x coordinate is doing as we move around our circle. Part B, give the value of tan theta. Well, tan we know is the opposite divided by the adjacent. So in our triangle, that's y divided by x. And if we use the results from part A, that means tan theta is y was sine theta and x is cos theta. And what we've got here is one of our trigonometric identities. This is a fact that is always true. I think it's also in our formula guide. Let's have a really quick look. We're going to go to section 3, identities. There we go. There is our first identity, tan theta equals sine theta over cos theta. Okay, and you can see we've got a few results here. We've talked about this idea of a negative angle being clockwise, and we've talked about these results. Take some time to read through that. I'm not going to do the reading for you. You can do that yourselves. Okay, then we're going to take a look at what these functions actually look like. So we're going to think about sine theta. That was our y value as we move around the circle. So let's start when our angle is at negative 90 degrees. Negative 90, I'm going to draw this in purple. Negative 90 is down here. What's our y value there? It's negative 1. Then 0, 0 is over here. What's our y value here? Our y coordinate is 0. So sine of 0 is 0. Next one is 90. When we're up the top here, what's our y coordinate? It's 1. So sine of 90 is 1. And so on. I'm going to keep on working around this circle. Sine of 180 is 0. 270 degrees. I'm back down the bottom of the circle, so it's negative 1. Okay, I'm going to fill the next couple in. You can check them on the unit circle. You can also check these values on your calculator. Make sure you're in degrees mode and just type in sine 270 and make sure you're getting negative 1. Similarly, we can do this for cos. So I'm just going to look at my x values. I'll start at negative 90. That was the first one. So negative 90 was this one on the left here. The x value is negative 1. Oh, hang on. Have I made a mistake here? Cos of... Oh, that wasn't negative 90 at all. I'm sorry. Negative 90 is down the bottom, of course. Yeah, that's negative 90 degrees. I've gone clockwise 90 degrees. And I want to find my x-coordinate. My x-coordinate there is actually 0. I might do one or two more as I made a mistake on that one. I want to find cos of 0. 0 is on the down here. That's my angle of 0. The x value is 1. I'll put that in here. I'm going to do one more. I'm going to go for 90 degrees. I'm looking at the top of the circle for 90 degrees. X value, x value is 0. Okay, and then I'm going to keep going. Negative 1, 0, 1, 0. Okay, of course, you can find those all in your calculator as well as another option. What we're going to do then is we're going to... Oh, I should probably have put all of those in sine and cos in different colours, but I'm going to plot these and I'm going to try and draw them smoothly. And what we actually find, if we find some of the in-between values, is that it has this kind of shape, which is called a sinusoidal shape, which is a fun word to say. So this was y equals sine x. I'm saying x because x is on the denominator there. I guess you could call it sine theta if you relabeled this as the theta axis. And then I'll draw the other one. Let's go for a different colour. So cos is going to start here. So I am going to draw it down there. Okay, and you can see that the cosine curve is actually the same as the sine curve. It's just translated 90 degrees to the left. So that is y equals cos x. Okay, so two curves, sine x, cos x, they look very similar to one another. Of course, plot them on your in the function app and make sure that they're looking the same. Okay, we've got a few actually there's only a couple of main trigonometric identities. We've talked about this second one, tan x equals sine x over cos x. The first one, sine squared x plus cos squared x, is another one that's really easy to prove or to show by going back to our unit circle. So this is where we said what cos x and sine x are. Because if we take that triangle, y, x, 1, it's a right angle triangle, so we know that by Pythagoras' theorem, x squared plus y squared is equal to 1 squared. And if I change x into cos and y into sine, we get this as another identity. You'll notice one convention is that we don't write cos theta squared, we write cos squared theta. And the main reason for that is cos theta squared is not the same as cos theta squared without the brackets. In the second one, we would be squaring the angle and then doing the cosine of that. So that we don't make that mistake, so that those brackets don't disappear and we start getting confused, we tend to put the squared before the angle. So when you see cos squared theta, it actually means cos theta, all of it squared. Okay, so that is the first identity. The second one we've already talked about. Looking at your graphs, you should be able to understand the third and fourth identities. Okay, so some facts about these. The graph of sine x and cos x, we can actually see from the one above, they repeat every 360 degrees or 2 pi radians. And it makes sense from our unit circle because once we've gone 360 degrees, we're back at the start. If we are solving an equation like sine x equals a number, maybe sine x equals 0.5, let me draw a 0.5 on there, you'll see that there's actually lots of intersections. So we'd need to check what kind of answers we're after. Is there some sort of domain for our function that helps us determine it? Is it something in the context that helps us determine it? But there might be more than one possible answer. In fact, there might be an infinite number of answers, so it's going way beyond having two answers from a quadratic. Okay, you will probably want to pause me and go through some of these examples on your own and then check your answers.